Hello. Hey, you know about atoms, don't you? Well, today we're going to look at an atomic model that's helped us understand a lot about atoms and their behavior. It was devised by a man called Niels Bohr. Now, he certainly wasn't the first to come up with an explanation about the structure of matter. That had been going on for centuries. The notion that matter is made up of tiny particles, which we now call atoms, has been around for at least a couple of thousand years. Today, scientists continue to explain matter, its structure and behavior, using different theories and explanations. In this program, we'll be focusing on the theory of Niels Bohr, who built on the ideas of other scientists, and worked with the best physicists of the 20th century to devise his atomic model, Bohr's atom. We'll take a look at the historical development of atomic theories, a brief outline of Bohr's life, the Bohr model in detail, parts 1 and 2, and beyond Bohr. A bit later, I'm catching a bus to meet some friends at the fun park. But first, I'd like you to come with me on a journey to visit a notable figure named Democritus, around 2,500 years ago. Although I've never really spoken to him. My Greek's not very good, you see. He was a student of a learned man called Leucippus. Together, they're regarded as the co-originators of the idea that all matter consists of individual particles, which they called atomos, meaning indivisible. It's from here that we get the word atom. Democritus said that matter exists because of the combination of atoms. They come into being when atoms combine in the right way, and cease to exist when atoms dissociate. But this view of the world didn't acknowledge the existence of a divine intelligence, and thus, right up until the 1600s, was rejected by the church, governments, and society in general. In 17th century Europe, there were challenges to conventional thinking. The scientific method was developed, which necessitated the backing up of assertions with evidence. In 1805, an English chemist, John Dalton, published conclusions from his research. Dalton proposed that all matter is comprised of atoms, which hold together by forces of attraction. Atoms are indivisible and cannot be created or destroyed. All atoms in the same element are identical and have the same mass. And atoms of different elements are able to combine in simple, constant ratios to form compounds. Dalton thought these indivisible atoms were hard spheres, but had no knowledge of their inner structure. His ideas were extremely useful to the science of chemistry. He developed a set of symbols to represent the elements, and using hydrogen as the reference point, estimated atomic masses of other elements. Over the next 100 years, it became apparent that Dalton's conclusions were not entirely correct. It was found that atoms are not indivisible. In the early years of the 20th century, physicist J.J. Thomson developed another theory to explain the structure of atoms by experimenting with discharges in gases. He concluded that there were two parts to atoms, a heavy part with a positive charge and negatively charged particles that were later called electrons. He likened the structure to a plum pudding, where the electrons were like raisins scattered throughout, held in by the positive charge of the pudding. Thomson suggested the repulsion of electrons created some order in their distribution. If there were two electrons, they would sit on opposite sides of the pudding. Larger number of electrons were arranged in rings within the pudding. One of J.J. Thomson's students, a New Zealander named Ernest Rutherford, who was a research physicist, tested Thomson's theory. His research, which involved firing positively charged alpha particles into very thin gold foil, led to his theory about the structure of the atom, which is known as the nuclear model. In 1911, Rutherford proposed that atoms consisted of a positively charged core, which he called the nucleus, and that electrons moved in random orbits around it. Smart, eh? Following year, 1912, the Danish scientist Niels Bohr visited Rutherford and set about trying to explain the behavior of electrons in their orbit around atomic nuclei. Bohr was a spectroscopist, and his work involved the analysis of spectral lines of hydrogen. Bohr concluded that electrons revolve around a central nucleus, but are found at certain distances away. These electron orbits are called shells. And you know what he found? That different shells have different energy levels, and electrons naturally occupy the lowest energy shells when an atom is in its ground state. The idea that all matter consists of small particles originated around 2,500 years ago in Greece. Democritus and Leucippus called these particles atomos, meaning indivisible. However, the Church rejected this theory. In the 17th century, the scientific method was developed. In 1805, John Dalton said atoms were indivisible. In the early 1900s came J.J. Thomson's plum pudding model. In 1911 and 1912 respectively, Rutherford and Bohr proposed their theories of atomic structure. First, a bit about the man. Bohr was born in Copenhagen, Denmark in 1885, where his father, Christian Bohr, was a professor of physiology at the university. His mother came from a wealthy Jewish banking family. His scientific talents were recognized and fostered early. His younger brother Harold became a brilliant mathematician. In 1911, Bohr received a doctorate at Copenhagen University, having previously won a gold medal from the Royal Danish Academy of Sciences. And in 1912 he moved to Manchester. Here he worked with Ernest Rutherford, studying the structure of the atom and building on Rutherford's cutting-edge research. He was among the first to see the importance of the atomic number of elements and its indication of the element's position in the periodic table. In the summer of 1912, Bohr returned to Copenhagen, was married, and continued his work on the physics of the atom, completing his theory in 1913, which was first published in Manchester. In 1922, Bohr's groundbreaking work was recognized when he was awarded the Nobel Prize for Physics. The previous year, Copenhagen University had established for him a new Institute of Theoretical Physics. He served as a director for the rest of his life. His institute soon became an international center for work on atomic physics and the quantum theory. Now, Albert Einstein was a great admirer of Bohr, but they didn't see eye to eye on some areas of quantum physics. However, Bohr always maintained that Einstein's objections to his ideas were very important in the evolution of his work. When Denmark was overrun by Germany in 1940, Bohr did what he could to maintain the work of his institute and protect Danish culture from the marauding Germans. He never made any secret of his anti-Nazi views. In 1943, under threat of arrest, he escaped to Sweden with his wife and some other family members in a fishing boat in the dead of night. Soon after arriving in Sweden, he was brought by the British government to the UK, where he worked on the project to develop a nuclear bomb for a couple of months before moving to the USA with a British research team. However, he was deeply concerned about the catastrophic potential of nuclear weapons and tried to persuade British Prime Minister Winston Churchill and US President Franklin D. Roosevelt to adopt peaceful policies on nuclear power. He continued to work in physics, promoting international efforts for the peaceful use of nuclear energy after World War II ended, until his death in Copenhagen in 1962. Bohr was born in 1885. He received a doctorate at Copenhagen in 1911. and moved to the UK to work with Rutherford. Bohr published his theory in 1913 and won the Nobel Physics Prize in 1922. During World War II, Germany occupied Denmark. Bohr fled to Sweden in 1943, then worked in the UK and the USA on the nuclear bomb project. He was a lifelong advocate for peaceful nuclear energy use. Remember how Bohr went to the UK back in 1912? While he was there, working with Ernest Rutherford, he recognized that physical and chemical properties of the elements depend on electrons orbiting the nuclei of their atoms. Rutherford had deduced that atoms were mostly composed of empty space. Protons were located in a minuscule nucleus, which contained most of the atom's mass. His work was based on research involving the firing of alpha particles at thin gold foil. Rutherford also proposed that electrons moved around the nucleus, but in random orbits. But scientists knew that when charged particles accelerate, energy is radiated as radio waves. In this model, electrons would be expected to lose kinetic energy and ultimately spiral into the nucleus of an atom because of the attractive force. The Rutherford atom was both mechanically and electromagnetically unstable, and it was Bohr who introduced new ideas. Know what he did? He worked on the analysis of the spectral lines of hydrogen. He chose the element hydrogen because it is comprised of the simplest atom. Bohr proposed in his first postulate that all atoms existed in a discrete set of stable or stationary states, with electrons occupying different shells at a certain distance from the nucleus, each characterized by a specific energy value. Bohr stated that no energy is emitted by electrons when in this state. This was a move away from conventional thinking in physics, which says that movement of any particle is associated with a loss of energy. Bohr called this state an atom's ground state, where electrons remain in their designated shells orbiting the nucleus. And not only that, Bohr gave the electron shells letters K, L, M, N, O, P, and Q. K being the first shell, closest to the nucleus, M the second shell, N the third, and so on. He said there is a maximum number of electrons that can fill a shell, defined by the formula. Number of electrons is equal to 2 times n squared, where n is the number of the shell. The K shell contains a maximum of 2 electrons. The L shell, a maximum of 8. The M shell, a maximum of 18, up to the nth shell. The valency of an atom is given by the number of electrons in the outer shell. It is the outermost electrons that determine the chemical behavior of an atom. As atoms get bigger, electron shells are filled in such a way that the first 2 shells, the K and L, are filled to capacity first. For the first 18 elements, hydrogen through to argon, the electron shells fill in consecutive order. The K shell with its 2, the L shell with its 8, and then 8 in the M shell. The K and L shells are filled to their designated limit before the next shell is started. But you know what happens then? Even though the M shell can accommodate up to 18 electrons with the 19th element, potassium, rather than continuing to fill the M shell, the N shell begins to fill next, once the number of electrons in the M shell reaches 8. Atoms of elements with similar numbers of electrons in their outer shell behave chemically in a similar manner. how quickly atoms form ions, and how readily elements react with one another to form compounds, their melting points, their conductivity, and many other properties, are determined by how atoms bond with each other. This, in turn, is determined by the way electrons are organized in atoms, and in particular, the arrangement of atoms in the outer shell. The Rutherford atomic model was helpful to scientists, but contained some flaws. Bohr introduced new ideas, building on Rutherford's model. Bohr's first postulate said that electrons orbit in shells with fixed energy around the nucleus. Shells contain a maximum number of electrons, which is equal to twice the shell number squared. Electrons in the outer shell are involved in chemical bonding and are called valence electrons. Valency determines many chemical properties. Bohr talked about atoms in their ground state. He said that when an atom is in its ground state, electrons occupy shells in a fixed position and with fixed energy. But he proposed that given suitable conditions, electrons can absorb energy and move from one shell to another shell of higher energy. An electron moved to a higher energy level is said to be an excited electron. This was described in his second postulate, which says that when energy, for example heat, is added to an element, it can cause electrons to move to a higher energy orbit. When they return to the original energy level, they emit a quantum of electromagnetic radiation. The word quantum can be defined as the smallest unit of energy. Bohr's work with electron emission radiation built on what had been recent research by German scientists Max Planck and Albert Einstein, who showed that electromagnetic radiation is given off or absorbed in a stream of small packets of energy called photons. Photons behave like both particles and waves. They have a quantifiable wavelength and frequency. After analyzing the emission spectrum of hydrogen, Bohr concluded that in order to move an electron to a higher energy level, the energy it absorbs must be equal to the difference in energy between the two energy levels or orbits. Because this is a definite and measurable amount of energy, the radiation emitted in the form of photons has a specific wavelength and frequency, and its energy can be calculated according to the equation E equals h times nu, which is a Greek letter. H refers to Planck's constant, equal to 6.626 times 10 to the negative 34 meters squared, kilograms per second. Nu equals frequency. When an electron is excited, it is unstable and quickly releases its quantum of energy to return to its ground state. The energy is released as light. Let's look at the hydrogen emission spectrum again. The colored lines appear because light emitted by the excited electrons is split up by the spectroscope. So when the hydrogen atom is heated, its electron absorbs a quantum of energy and moves to a higher energy level, becomes unstable, returns to its ground state, and releases electromagnetic radiation in the form of a photon. The light is split up by the spectroscope. Each element has its own unique emission spectrum, which makes it possible to identify different elements. If a beam of white light is shown through an atomized sample of an element, then an absorption spectrum is formed. This has a series of black lines unique to each element. The black lines are frequencies absorbed by the element. Bohr's second postulate says that electrons can absorb energy and move into higher energy shells. These excited electrons return to their ground state quickly and release electromagnetic radiation as photons. Photons have a specific frequency and wavelength. Bohr's research involved the use of hydrogen emission spectra. Because elements have unique spectra, spectroscopy is used to identify substances. Now, Bohr was a clever man. His model was, and still is, very useful in understanding atomic theory. It uses pieces of both conventional and quantum physics. It explains emission and absorption spectra in a way that is easily understood. Frequency of radiation can be quantified and measured, and mathematical models used to calculate specific amounts of energy absorbed and released. For example, with the hydrogen emission spectra we looked at earlier, using a mathematical formula that tells us the actual energy released is equivalent to negative 2.18 times 10 to the negative 18th power joules divided by n squared in this particular example, we can quantify the actual energy release between different electron shells. But it wasn't a perfect theory. One of the flaws of the Bohr model is that such mathematical predictions are only completely accurate with hydrogen. There are inconsistencies with elements containing atoms larger than hydrogen. There are other questions it couldn't answer, like why are electron orbits circular and not elliptical? Why do the energy shells, in which electrons orbit the nuclei of their atoms, have specific energy levels? In 1926, the German scientist Erwin Schrödinger suggested that when electrons are orbiting a nucleus, they behave like waves. Using this, he was able to accurately calculate and predict the energy levels of not only hydrogen, but of larger elements. Schrödinger's atomic model is known as wave mechanics or quantum mechanics. It is the basis of how we understand and explain many properties and behaviors of atoms today. He built on Bohr's model by proposing that within the various energy shells of atoms are energy subshells. Schrödinger numbered energy shells rather than give them letters. But the subshells he identified by assigning them lowercase letters: S, P, D, F, and G. The Schrödinger model has enabled scientists to make more complex and accurate predictions of atomic behavior. Bohr's research broke new ground on a number of fronts. It used pieces of both conventional and quantum physics. It enabled emission and absorption spectra to be explained, and for energy emissions to be quantified. But the mathematical models used by Bohr were not consistent for larger atoms. They were still unanswered questions, and research continued. In 1926, Schrödinger described a quantum mechanics model where he proposed the existence of electron subshells. Well, I'm just about done. I'm off to join some friends at the fun park. The evidence suggests my bus is running late. Not difficult to test that hypothesis. Just as I thought. Pretty scientific, eh? The scientific method involves rigorous testing of theories by gathering evidence. A couple of centuries ago, John Dalton provided us with a scientific theory that helped to explain the properties and behavior of matter. While Dalton wasn't the first to suggest that matter was made up of tiny particles, he paved the way for many other chemists and physicists to build on his work. One of the most significant of these scientists was Niels Bohr, who was the first to propose that electrons moved around their nuclei in distinct orbits that have specific energy levels. Many more ideas have since contributed to our body of knowledge about matter and atoms. But Bohr is remembered as a major influence on the thinking of today's scientists and was responsible for moving the science of chemistry into new areas. And speaking of moving into new areas, here's my bus. Looking forward to the fun park. See ya.